Ready? Yes, whenever you are. So, welcome, everyone.
Thank you.
I hope we enjoy a lot in this session. We are going really deep into the Kubernetes networking. As you already see, I published an article about it. Maybe some of you already know about the article and also the Kubernetes networking and the Kubernetes itself. But if you don't know, you can leave the session right. No, I'm joking. If you don't know, I will explain a bit about the Kubernetes basics. What we need here, actually, not all the basics here, but what we need here. And then we'll go through the subjects step by step. Um, I think we can start. Someone asked about the time. I think it was Thomas. Uh, no. Yeah. Okay. So, yes, Kubernetes networking. This is the most difficult part in the Kubernetes. So be aware if you do not understand that much, don't worry, because it is what it is. And sometimes it takes time to understand all of it. And it needs more knowledge about the routing, about the basic networking. So uh, I I do my best to explain as much as possible during this 1 hour session. And I have also my remarkable tool to draw what we need because I always prefer to draw something. Explanation would be easier for me at least. So, why Kubernetes networking? Because yeah, this is the most difficult part in the Kubernetes, and also I really didn't find why I wrote this article, because I didn't really find a good article about this to put everything together, how networking is working, how the load balancing is working in Kubernetes, what is the BGP, what is IPVS, IP tables, what is the responsibility of kube proxy here, the node port, and everything. So it is difficult to put all those things together. I wish I could have a Kubernetes cluster here, but I forget to run the AnyDesk on my laptop at home to just show the Kubernetes cluster, uh, and I don't have it on this on the company laptop. So maybe in the next session, if there would be any next session, we could do that, because yeah, that would help much. Yes. So we are going to talk about the IPVS, IP tables, pure LB, metal LB, overlay, underlay. I just saying this word to make it familiar. Node port, load balancer, kube proxy, CNI, and BGP, and much more. We are going to talk about how pods in Kubernetes talk to each other when they are on the same node, when they are on different nodes, uh, how it's going to happen when you call a IP of another pod, or call a SVC service from another pod, how it's going to be routed in the cluster, and yeah, everything about this stuff. Everything is network here. So before I start with the CNI and load balance controller and kube proxy and these components, I want to just go through the basics of Kubernetes and just say what is pod, what is a container, what is deployment, stateful set, services, and the component of a Kubernetes cluster. To do this, I use my Remarkable to also draw pictures. So as we had already Docker sessions, I expect you guys in the in our office to know more about the CNI, CRI. So I'm looking at your face and you don't know. Okay.
No, can you remind us, please?
Yes, no problem. So as we talked before, we have a Docker host. And in the Docker host, we have networks and we have containers. Okay. We said who is responsible for creating the containers, the networks, the storage, and there is a Docker daemon for that. So Docker daemon is responsible. But Docker daemon talk to which component? Talk to container D, for example, most of the cases. And the container D is responsible to create the containers, allocating IP addresses and other stuff. There is also a plugin for networking for storage in the Docker, but also and we call it CNI for a networking, and it's responsible to allocate the IP address, to routing the traffic, to create a bridge, to create a virtual bridge in our host, in a Docker host. So CNI is responsible for that, which we use it in a Kubernetes. So in Kubernetes, we have a CNI plugin, which are responsible for these actions, and it can be Calico or other plugins. Not mostly, but yeah, mostly we use Calico because of some features in Kubernetes. Right, like this. So we also have network in our Docker host. And we said each container has its own namespace. And because of that, we can separate our environment, our containers from each other. Because of the namespaces in the Linux, in the kernel. It's a feature of the Linux kernel, namespaces. And there are different namespaces. It's different from Kubernetes namespace. So don't think about that. But the namespaces in the Linux kernel is something that separate your container from each other. So we have a IPC namespace, we have a storage namespace, network namespace, user namespace, and other namespaces. So we also have namespaces. I'm mentioning these because later we need it. And other than namespaces, for a Docker that I can mention right now, so we learned if we want different containers talk to each other, they should be connected to one network that is created by us. If we want to call the Dockers, the containers, by their names, you can, you can call their IPs, you can ping their IPs, connect through their IPs. But if you want to connect to their names, they should be on the same network. So you should first create the network, then assign this network to the containers so they can attach and they can see each other in that network, because you are creating a shared namespace for that network that everyone are participating in this namespace. Yes, this is network of containers, so containers can connect to each other like that. I'm thinking if something else is important, you can also remind if there is anything else. Yeah, let's just pass. So we have Kubernetes. And under Kubernetes, yeah, one more thing about the containers. We also said containers are nothing more than processes in Linux. So if you have a container on your Linux, on your host, there is nothing more than a process that is isolated by namespaces. So this is also important for us. So in our Kubernetes, we, despite from the Kubernetes components and the features, the underlay, the infrastructure is a Docker, is containers. So it's yeah, in the previous years, maybe you heard about the replacement of Docker in the Kubernetes, and in the news, uh, it was like a bomb that, hey, they are going to change the Docker, and what's gonna we do? And the answer was nothing, because Docker itself is nothing, and this is the container D that is important. Hey, see you. Have fun. Good evening. Good weekend. Yeah, you too. So Kubernetes removed the Docker because it's extra. When we can use the container D, why we should use Docker? It's extra layer. So uh, it connect to container D to create the pods, create the containers. So what is the difference between pod and containers in the Kubernetes? In Kubernetes word, we never say uh, container, because the basic layer is pod. The first level is pod, and the pod can be one container or multiple containers. So in the pod, there can be one or more containers, but we never say container. We always say pod. In the Docker, it is container. In the Kubernetes, it is pod. And when you create a pod, you also need a service, which we call it SVC in short, to specify the networking, the port that it can be exposed. You remember in the Docker, we had to expose the container to reach it from the network. So here we also need a SVC. We need a service to expose it to others, to specify the port, which port should be connected to what container port. So yeah, and the SVC and the pod is connected to each other by labels. So if your pod has label of app transport, your service should also have app transport label. So this way they connect to each other, which I will come back later to this point, but yeah, just get it right now. This is some basics. I'm doing my best to explain it. So this way they connect to each other, and that's it. That's the basic things. Let's me think here. So yeah, okay. Let's go through. First, we have a component. Oh, you don't see it. We have a component in Kubernetes called kubeproxy. Because we don't have a Kubernetes cluster with one node. We have it, but we don't use it in production. So because it's a cluster. So we have a kubeproxy, which is responsible for mainly networking in other nodes. So we have our cluster like this, at least with 3 masters and several worker nodes. And when you deploy your pod, it will be deployed on worker nodes, not on the master. Master is only responsible for the Kubernetes itself operations. But the worker nodes are responsible for the workloads like pod. And kubeproxy will be in all nodes to manage the networking of the nodes and the cluster itself. So it's also here, also here, also here. How kubeproxy will manage it? By applying the rules to the node network. So if you need a network interface, if you need to route something, kubeproxy will do it. How? We will do it. Maybe I will explain it later. But this is right now how it is. And load balancer, if you have worked with Kubernetes, you probably noticed that we have different services like node port, like cluster IP, like load balance. Why? Because the cluster IP is internal. So when you choose a cluster IP service, you can internally access it through your cluster. When you have a load balancer, you can call it from the outside with a load balancer IP, which you get from the cloud, or you will get it from the uh, from the pool IP you specify. How can I? Yeah, this way. And we also have the node port, which give you a port and give you an IP of the nodes. So you can call that and get to your pods. So we have these 3 types. So now you can understand we have a load balance controller to manage the load balancer stuff in the Kubernetes. We have a kubeproxy to manage the networking stuff in Kubernetes. And we have a CNI because we also have at last there are containers. So there should be a CNI to manage those containers, the networking. But this will come to your mind. If we have a CNI, why we need a kubeproxy? Why we need a load balancer? The thing is, CNI configures a network interface for each container. And CNI works in 2 models, encapsulated or overlay and unencapsulated underlay. What do we What do I want to say about the encapsulate, underlay, and overlay? With overlay, if you know, let me go for it, a lot of basics. This is a PC1. This is a PC2. Who remember the OCI layers? Do you remember? Anyone here? We had a data link, and basically we had MAC layer 2, and we had layer 3, which was related to IP. So the data link was the physical, and the MAC address was the MAC address, and the IP was, we call it layer 2 or layer 3. And those PCs could connect to each other through the IP, their IP, but how? With a MAC address. If we do not have a MAC address, we cannot connect through the IP. And because the ARP, there is an ARP protocol. What was the ARP? Address resolution protocol that find your IP through the MAC address. So if you don't have MAC address, you cannot get an IP for your PC, because it should be registered somewhere in your laptop or router or switch somewhere that can be routable. So we have a MAC address layer 2 and we have IP on layer 3. When we say here overlay, because we know nowadays everything is on layer 3, we talk about the IPs every time, we call the IPs, but in Kubernetes and maybe other technologies, we use VXLAN or IPsec, and it's layer 2 over layer 3. So we said we have MAC address, layer 2, layer 3, and in overlay, on top of the IP, we have again MAC address and layer 2. So it will be routed on layer 2. I will come back to it later. So just keep it in mind. Layer 2 is isolated, so there isn't any need for routing distribution because it generates IP header provide in the IP package, and when you connect to the bridge, it connects to your workloads, to the pods, and it's much easier to connect to your pods through this layer 2, because you don't need the routing. It will happen on a table, on the bridge, and it will route everything to different pods. Unencapsulated, this is a layer 3 network, as we expected. Unencapsulated, it's not capsulated to something. So there isn't any encapsulation here. It's layer 3, routes packets between containers or pods, and the worker nodes need BGP. It's a routing protocol that manages the routing. So it knows where this pod is located, on which node. So because you can reach pods through different nodes. If I connect to the node 1 and my pod is located on node 3, it could be also reachable. So this is the BGP responsibility, or any other routing protocol responsibilities like OSPF, EIGRP, or anything else. So this is a BGP responsibility, and this is underlay networking. For example, here you see pod 1 and pod 2 on the node 1, which is connected to the custom bridge, which the CNI create the custom bridge, and those pods, those, let's say, containers connected those, so they can see each other through the CBR, through the custom bridge with their MAC addresses. So if you call the pod 2, it never translated because the bridge know this IP is belong to which pod. So it goes through the bridge and it will find it through the MAC address. You know how it looks like. You are in pod 1 and you ping the pod 2 IP address. It goes through this through the bridge, and in the bridge there is a list of the IP addresses and MAC addresses. If uh, it match, if the IP match with a MAC address, then the bridge knows, okay, I have this IP on my side. It is attached to me, so I can route it to route these packets to the destination because I know this is the destination. But when it doesn't know about it, it goes through the routing table. And here we have the BGP routing. It's connected through the nodes. Each node has its own BGP routing, and they connected with Bird and lots of other stuff. Here it was, it's encapsulated, but when we have an overlay, it goes through the custom bridge. It doesn't know here, for example, here in pod 1, we ping pod 3. By ping, I really don't mean ping because it uses a different protocol, ICMP, rather than TCP and UDP. But I just want to mention we want to connect to pod 3. So in pod 1, if you ping pod 3, it goes to the bridge. It doesn't know where the hell is the pod 3, so it goes through the routing table. So the routing table must know not the pod 3 IP address, but knows the range, the network range of this pod address. So according to routing table, it sends the packets to the destination. In the overlay, we have the again the encapsulated, which was the layer 2, and in the layer 2 we have a IP tunnel, and those tunnels between nodes are connected to each other. So the routing table send the packets to the tunnels, and since the tunnels are connected to each other in the cluster between nodes, they know where it should be, where is the destination. So it is possible that the CNI uses both architecture, encapsulated, overlay, and underlay. I know it's a bit difficult and confusing because it also took me a lot of time to understand everything, but I'm doing my best to explain any details in in 1 hour. Yes, load balancer controller. As we said, we can have a load balancer type for SVC, for the service in the Kubernetes, and Metal LB, Pure LB, and other services providing us with this functionality of load balancer. And when we create a load balancer service, this controller provides an external IP which is routable from the outside. It's like a public IP or an IP that a node can have. My English sometimes, finish soon. Yes. And this IP will be assigned to the physical network interface of the node. You have an IP address for your node, and you can also have a secondary IP address beside that one and attached to the same interface. It is possible in the Linux and also in the Windows. So this secondary IP address for the load balancer will be attached to the node, to the primary interface. And this allows the BGP router to get it, to know, okay, you have this IP address and I know it should be routed where. So it will keep it and update the routing table in the BGP, which this IP address is belonging to which node, to which MAC address, because we said MAC address, IP address, they are connected to each other. So when a new IP is assigned, in the case of an overlay network, IPVS or IP tables, these are both similar but different technologies, will be adopted. In the case of an underlay network, a routing table will be adopted additionally. So, like here, like here, on the top we have node 1 and node 2. No. Yeah, this is separated. Node 1 on the top. What we have here, we have a load balancer IP, and we have IP tables. IP tables is a firewall in Linux, which is responsible to do the NAT, the destination NAT, the source NAT, the load balancing. Also, it is possible to do load balancing with IP tables and IPVS, similar things in the Linux. So when we say IP tables, we mean firewalls, basically. You can ban a port, and you can open a port, and you can do lots of things. You can control the network limit. You can control basically anything related to network that is coming or going out from the nodes. So the IP, the load balancer IP, is connected to the node, and it goes. If you see here, we have an ETH serve. It's a Persian serve 0. We have ETH 0 as a network interface of our node, and as a secondary IP address, we have this load balancer IP. And after a packet, a connection comes through the IP, it goes through the IP tables, because this is how is architectured in Linux. Any packet coming or outgoing should be passed through the IP tables. So it comes through the IP tables and then goes through the routing tables in Linux, and the routing table decide it should stay in this node or it should goes out. And since it's inside, it goes through the bridge, which is in this node, and bridge knows this IP belongs to what pod or what MAC address or container. In case, on the picture below, in case it goes through the different node, for example, here, it come to the node, it doesn't matter, node 2 or node 1, but the pod exists on the other node. So what would happen? It goes to netfilter or IP tables again, and it goes to routing table. So routing table knows, okay, this is not mine. I will pass it to the another node. And I know what is the node because I know everything about the nodes that are connected to me. Because BGP is updating me every time. So, or we have overlay network. the tunnel is connected. So I know everything. So after it goes to IP tables and after it goes to routing table, routing table send it to the desired destination, desired pod that we want. So what the hell kubeproxy do here? If everything is done by IP tables and the CNI and the load balancer as this thing, actually the kubeproxy only maintains the network rules in IP tables or IPVS. In Kubernetes, I think I wrote it somewhere here. I want to mention it now. Yes, as I remember. In Kubernetes, services, endpoints, node ports, load balancers are nothing more than just rules in IP tables. So if you create a node port and it opens a port for you in Kubernetes, it doesn't mean that you that a port is opened on node. If you tell net the port on node, you will reach to your destination. But when we say I want to open a port on node, it means behind it there is a service that is listening on it. And on nodes, because you don't know this pod is deployed on which node, it can be on any node. So you cannot open this port on each node, because then you would need a service on each node to listen on this port. So in order not to do that, we define IP tables rules that defines anyone who wants this port route it to this destination. So this way, you do not have any service to listen to this port, but you have a rule on your IP tables that if someone wanted to reach this port, okay, route it to this IP and another port. So this is important. And kubeproxy basically is responsible to maintain these rules. So if you create a service in Kubernetes, it's a rule in IP tables. If you create a load balancer IPs, it's a rules in IP tables. If you create a pod, it's also a IP tables rules. The IP tables will be updated. Also for deployment, stateful set, and most of the things. So the IP tables is under pressure. Everything's going through the IP table. So this is important. And behind the IP table, there is net filter module in the Linux kernel, which is mainly responsible for those rules. So like Docker, we have the container D, we have IP tables, and behind that, net filter, who is mainly responsible for that. And yes, why I mention always IPVS? Because it is because of the performance. The performance of IPVS, which do the same as IP tables, is much better, and it supports more load balancing algorithm. With IP tables, you have round robin, one this, one this, one this, one this. With IPVS, you have different algorithm, load balance algorithm, based on the hash, source hash, based on the round robins, based on the least connections. So it is important for us to manage these things. I wanted to write, I also want to write an article about the service mesh in Kubernetes and how it's managed with the networking. because it's also an important thing. Service mesh is also responsible for the networking in Kubernetes. And when it comes with the IP tables and the whole networking in the Kubernetes, it will be interesting and more complicated. So the networking world is really complicated. Don't feel bad. So turn on your Docker Compose and let's go. Let's move forward. We said we don't. I don't want to mention this. So summary: kubeproxy maintains the IP tables. CNI provides the common interface, underlying networks, routes traffic to desired destinations, and performs other related functions related to the containers. Load balancer controller, it's for load balancing functionality and update the host interface for the secondary IP address. So that's it for the first part. And the second part, which I basically explain it, but we just now see the pictures. Pod to pod or container to container, single node on a single node, and IP address space. So you call an IP address of another pod on a single node, on a same node, which I said it comes through the virtual interface here. Yeah, virtual interface. When you create a, let me show it. When you create a container in Docker, you have the bridge beside in I have Docker network ls. I have two bridge here, OPS default and the default bridge. And if I list my interfaces in Linux, I have also two bridge here, this one and this one. And this is my physical interface, basically, in this VM virtual machine. And these are the bridge for the Docker. But when I create a so this bridge you see here, Docker 0, or this bridge is basically is this one you see, CBR 0. And the container itself has its own interface, because each container should have their own interface to be able to connect to be able to connect to the network. So here, when you see the pod, it has their own interface. Who created? CNI is responsible. And it's connected to the bridge. But what happened when we have two containers in one pod? As we said, we separate the containers with namespaces. When you have a pod, you have one namespace for what amount container you have. So if you have 1, 2, 3, 4 container in one pod, everything is shared. Network is shared, storage is shared, and you see the same thing. So because of that, we never say pod in Kubernetes. We never say container in Kubernetes. We only say pod, because this is what we want. So one pod, one network namespace, it connects to another pod through the custom bridge using the IP, using the list of IP and MAC addresses, which the bridge knows about it. So it's easy. You call it, the bridge decides to pass it over to which container, to which IP address. That's it for this. And one important thing, Yes, when we create a container, when we create a pod in Kubernetes, a hidden container will be created on the underlay, on the container D, on the node, and this is pause container. It's responsible to hold the pod namespace, and it will be there always. You don't see it on the Kubernetes side, but you will see it on the node itself. So if you go to the node, if you get the list of the containers, you will see there is a pause container per pods. So I just wanted to mention it, that have it in your mind that there is a container which is responsible for everything, namespaces in the pod. On third section, we have the same thing, pod to pod, container to container. We had the second, yeah, container to container, but with multi-node. Again, IP address base. So what does it mean? As I explained it before, the IP, for example, you want to reach pod 4 from pod 1, you ping the address, it goes through the bridge, it doesn't know, shit about it. It's routed to the IP tables because it doesn't know anything. So it will be decided in the node, in the routing table and everything, that yes, I know where I can find it. It will be routed to the node 2. It goes again through the interface, through the IP tables, and it will reach the bridge, and then bridge decide to hand it over to which IP address. And again, you will reach your pod 4. Let me see what is here. Yeah, it's also mentioned here. ARP fails because there isn't any IP connected to that bridge. Basically, this is what I mentioned. And number 4 is service IP address space. Yeah, because in Kubernetes, we never, or in Docker, we never call another pod or container with their IP addresses because it changed over time. We call it by their service or their names. So if I call a service, then what would happen? What would happen? Who knows? If I call a service in Kubernetes, for example, you call a SVC4, service 4 in Kubernetes, and you are on pod 1, then what happened? How it's gonna be routed?
Guess it's going to be mapped somehow from the service into the IP address, and then the same as we described before will happen.
Yes.
But I don't know why the mapping is happening.
Yes, that's correct. We first need to do a resolution. It's like internet. You call Google, but what is behind it is the IP address. So there should be a DNS to resolve this address. In Kubernetes, there is a default kube DNS or other services to resolve these things in the whole cluster. And you can also have your own DNS service, like name dbind, and you can add it to your Kubernetes and call anything you want and reach it. So when you call a service, it will be resolved to the IP address, and it goes again, as you said, through the bridge, through the IP tables, and again the IP tables there. But there is a bot here on the node 2. You call the service SVC4, for example, and this pod exists on the node 2. What happens if in this pod or different pods are connected to this service? Because it is possible. We have a replication of pods in our Kubernetes. We can have a deployment or a stateful set of 4, 5, 10, 100 pods, and with one service. So one service would be responsible for all these pods in the Kubernetes. So if something comes to the pod, something comes to the service decides which pod is suitable. How? It's what happened in IP tables. As I mentioned before, we have the load balancing algorithm. So it can be round robin, it can be least connection, or any other algorithm in the IP tables. So I want to reach SVC4 IP table, decide based on the algorithm which pod is suitable. Then it will route it to the best pod, best option, based on what we want, based on the algorithm. So that is the important thing to have in your mind. But I will, I describe it here. I think I don't know. Is it backend? The SVC destination. The destination pod IP address. But how? Yes, there is a but. But how? How services? Because we said service is attached to pods with the labels. So it means they don't know the IPs because it's assigned with labels. But there is another workload called endpoint in Kubernetes, which is responsible to get and store all the IP addresses related to the service. So service attached to the pods and select the pods with the same labels and update the endpoint with those IP addresses. So then you know this service has these IP addresses. So it will happen again and again and again during time. So each time the service update the endpoint using the pod IP addresses. Because of the label, they know which pod belongs to which IP address.
So the DNS we were talking about before is endpoint?
No, that's the different. That's the different.
Right.
Yeah. That's a necessary for going out, but when you going up, it's like north to south and south to north connections. So you are going out, you use the DNS, you don't need the endpoint. But when you are coming up from the south to north, you want to know this service has which IP addresses. So here, the DNS doesn't help you because in DNS you get one IP address, not multiple IP address. Okay, and when you resolve it through the DNS, you get the service IP address, not the pod IP address. So when it comes to service, then service knows the IP address of pods.
Yeah.
So the DNS, that was a good point. The DNS is responsible for the services IP addresses, not the pods. And the service is responsible for the pods IP addresses with the endpoint. That's a good point. Thank you. Yeah, as we talked about it. So are you ready for the big picture? That's time. We have 2 minutes. If you guys have 5 minutes more, we can finish it. It's not that much. But I will also upload it as we did it on YouTube, or in our also in our team channel, so everyone can access it later. So if you want to leave, you don't have time, you can do it. So far we have one node here. We have different pods. You see it, yeah, it's small for me. We have different pods here, pod 1, pod 4, pod 2, pod 3, and they are connected. For example, pod 4 and pod 2 connected to one virtual Ethernet because they have one SVC. So the SVC is the virtual Ethernet on the nodes. It's an interface because we said pod IP address, SVC IP address, node IP address. So these are all connected. So the pod should be connected to the service through the IP. So it means the service also need a IP address. So it should be routable because the DNS is using it. So we need a virtual Ethernet, not a real Ethernet, not a real interface. We need a virtual interface for our service because it should be routable in our network. So we have a virtual Ethernet for the service. So pod 4 and pod 2 is connected to virtual Ethernet 0, and the other one have their own virtual interface. And as you see here, Kube IPVS bridge, we have a bridge that connects all these virtual interfaces to each other on the same node. So each node has its own bridge, which connect to the services, and services connected to the pods. And then we have a routing table here, which will be updated with the BGP. Actually, BGP will update the routing table in Linux. We said how? We said BGP is mainly responsible to know about the IP addresses in nodes, know about the IP addresses for SVCs, for pods, for other nodes, and for the node itself, the primary and secondary IP address. So when it gets all the IP addresses, it updates the routing table, because then you would know which node is responsible for which network IP address. So for example, in the Kubernetes, it's also a good thing to know. If I share it, lots of things in my mind. So we have node 1, we have node 2, we have node 3. It's not sure. Come on. Present with share screen. Yeah. So here it is a Kubernetes cluster. We have node 1, node 2, node 3. And each node has its own IP address. Yes. And we specify a network CIDR for pods, for SVCs for pods. With the CIDR, I mean something like this/24 or 16 or anything. How Kubernetes handle it? It will specify a range for different nodes. For example, 1, 9, 2, and 8 is for this, and 16 for this, and 32 for this one. So in this way, the routing table knows if the pod IP address is 192.168.1.6 and 4, it should be on this pod. So it will be routed to this on this node. It will be routed to this node. So this is important. So here the BGP is responsible to update the routing table because the routing table should know about the routings and the IPs of other nodes. There are other nodes. And these BGPs on different nodes talking to each other continuously. It calls BGP peering. They always talk to each other to update each other about the nodes, about the IPs, IP addresses. This way, they can handle the networking. Here we also have the overlay IP tunnel, which is also, we said it's connected to another tunnel on another node. And we have IP tables or IPVS rules, which we said it's important for our services, load balancers, endpoint, anything related to the Kubernetes. It's really important and will be updated by kubeproxy, the IP tables rules. And then we have the actually the interface of our nodes, and the load balancer also update the interface of our nodes. And yeah, because the IP should be routable from the outside. And pure LB or metal LB is responsible for this load balancer controller. And that's it basically. That's it basically. And here, let me see. Yes, if a packet comes through the load balancer IP, then it goes to the node port. Then in the node port, it's an IP and a port, which will be translated by IP tables to the right direction, which can be a service. So then it goes to the service. The service knows the endpoints. And if there is an ingress controller, if there is a, I don't know if you know ingress controller in Kubernetes or not, but it's like a reverse proxy. It's like a node that you have. You connect to this node, and this node knows, for example, /API should be routed to which pod, and /application should be routed to another pod, and /transport should be routed to, I don't know, pod 4. So ingress is mainly responsible for reverse proxying. So when you are outside, you call this you call the URL with I don't know, transport. It will be resolved to the load balancer IP address, node port, come to the service of the ingress, because we are calling the ingress with that URL. And after the ingress, it again goes to the service IP, because ingress doesn't know shit. It just know about the service. It knows /application should go through which services. So it goes through the service, and service knows about the endpoint, and again it's routed through the pod. That's a bit difficult, I know. That's a lot of information. And yeah, this is the networking, how some part of the networking in theoric, but Yes. How does it feel to get that much information in 1 hour?
I will ask a lot of questions, but
Yeah.
another time.
You can, yeah, I see the link face, but you can ask me questions later in the chat.
Yeah.
Because maybe this is others' questions, and yes, we could manage it with 8 minutes delay, and yeah, that's it. That's it, guys.
Yeah.
And
Thanks.
I hope you enjoyed.
It was intense.
Yeah, definitely. And it was a bit. I know it's difficult. Always networking is the difficult part, because with other things, you can really learn it fast. It's a deployment. It's a manifest. You replicas, labels, and everything. But networking, you need a lot of things to know. But I did my best to transfer at least what I can.